This is the second part of the series. As we know, UCIe 2.0 spec document mentions or supports uh, three package modules: standard package module, advanced package module, and 3D IC module. In continuation to my previous session, here I'm going to list some of the differences between standard package module and advanced package modules. Let's look into three packages. Uh, this image shows how the bump size and bump pitch reduced over the period. C4 was more solder bumps, whereas C2 are copper pillars. So as the bump pitch reduced, the interconnect density also increased. So we can broadly, classify this, uh, interconnection bump technology into three generations. In the first generation, they used, the highlight uh, uh, lead solder bumps with pitch exceeding more than exceeding 130 microns. Uh, C4 was the technology, controlled collapse chip connection. So 2D packaging, multi-chip modules, they are like utilize this C4 pump technology. The second generation, we also call it as a C2. So it introduced microbumps with a pitch ranging, from 40 to 130 microns. This technology is widely used in today's packaging technology. So C2 stands for chip connection. So 2.5, this generation is also called as, this packaging is also called as 2.5D. The third generation, now also called as 3D IC, achieved a significant reduction in bump pitch to below 130 microns, enabling advanced 3D chip integration. So what is the main difference is, in the first generation it is solder bumps, third generation it is the copper pillars. In the first generation, the pitch was greater than 130 microns bump pitch. The second it was 40 to 130, and the third generation it is lesser than 30 microns. That's in summary. So yeah, let's look into the UCIe specific packaging. The first image, it shows we have three dies sitting on a package substrate, and we have a traces connect passing through the substrate connecting dies. So standard package, it involved 2D packaging. It implies traditional packaging with larger pitch. For example, UCE talks about the pitch of UCE spec document talks about pitch of 100 microns to 130 microns for this standard package. So these use solder bumps or C4 bumps, we call it as. Uh, let's dig into this advanced package. Advanced package is also called as 2.5D packaging. This technology uses microbumps, also called as C2 bumps. The bump pitch is around 25 to 55 microns as specified in the UCE spec document. So this utilizes advanced package technology utilizes advanced packaging technologies like EMIB, COWS, enabling higher density and performance. Example of this, for example, here in this image, right? We have we have this silicon bridge, sitting on the substrate connecting two dies. Okay, we have a substrate, we have a silicon bridge. Okay, and in the second example, we have additional thing here, substrate here. Sorry, interposer here. In this case, let's consider it as a silicon interposer. And this traces, right? These traces, they connect two dies which are passing through the interposers. Of course, when it comes to connection here, TSPs are used, through silicon wires. They're longer, thicker wires, vertical wires, and of course passing horizontally also through the interposer connected two dies. In the third example, right here, we again here we have a silicon interposer. In this case, it is organic interposer, not a silicon interposer. But a different, what is the difference is we have a separate silicon bridge connecting the two dies. Okay, uh, this is an example how this way someone can realize the advanced packages. These are some examples. The third, the package module which specified in UCIe spec document is 3D IC. I mean, spec 2.0 supports 3D ICs. Okay, it's also called as 3D packaging. The bump pitch in this case is lesser than 10 micron for optimized, but typically for functional it is 10 to 25 microns. Okay, as specified in the spec document. So the channels are here, the vertical channels. For example, here, right? So these are vertical channels. So the one is upper is this one is a die, this one is a die. The dies are stacked one above the other. The interconnections, day-to-day connections are vertical. The channels are vertical here. Um, yeah. So but the dies connected to the cipher still remains. Dies connected to substrate still remains C4, but day-to-day connection is happening through microbumps, which are as whose pitch is 10 to 25 microns vertical channel. Now let's look into some of the characteristics of the UCIe packages. The first one is a channel range. Okay, so what is channel range? It is the maximum distance over which high-speed signals can be reliably transmitted between chiplets within a package. The long reach standard package supports long reach. It means up to 25 mm. Okay. For example, look at this diagram here. I mean the image here. This is one die, and say for example this is one die. The distance between them, the maximum distance, that is a channel reach. Maybe this way also, the maximum distance is clear, right? Okay. So standard package supports a long reach up to 25 mm, whereas advanced package does not support long reach. UCIe 3D also not meant for long reach. This is a cross. One is a the first image is the top picture, top level view, and the second image is a cross section of the same 2.5D IC, where you have a different chiplets sitting on a interposer, and again through C4 bumps are connected to the PCB substrate. Okay. Uh, a 2.5D typically uses micro bumps for between the dies and interposers. Okay. So coming to the short reach, right? The standard package supports short reach up to 10 mm. Okay. Whereas advanced package supports short reach as up to 2 mm. Okay. UCI 3D, this is meant for vertical channels because it's 3D is about stacking the dies, right? So the image, helps us to visualize. For example, this is one die and this is a second die, right? They stacked one above the other. Okay, the face-to-face hybrid bonding is done between the two dies. Okay, so typically this height is fixed, and the 3D packaging. This is meant for vertical channels. Okay, again, both the dies together, sits on the substrate with through C4 bonds. Now let's look into second difference, the number of lanes. Now we can also calculate the width of each cluster. This image, it's a day-to-day, connection for a single pack, the standard package. It supports 16 single-ended data lanes. It's also referred to as X16. Okay, this image, second image, it's a advanced package module where connecting the two dies. It offers we can call it as UCIe. Okay, it offers 64 single-ended data lanes, also referred to as X64. Okay, so let's understand what are these. We also have additional, the lines, additional, the signals moving here and left, right, and right to left, right. So data lanes, right? Data lane. Till now we are talking about test. UCIe standard supports 16 data lanes. UCIe supports 64 data lanes. So data lanes, they carry primary data signals from transmitter to the receiver. As you can see in the image, right? So we have a 16 data lanes from transmitter to the receiver. Here also again 16 data lanes from transmitter to the receiver. Okay, 16 and 16. Okay, for each die. Okay, each die contains 16 data lanes, from transmitter going out to the receiver. Moreover, it also contains the clocks. Okay, so the UCIe interface uses clock forwarding. Clock forwarding means the transmitter, the clock from the transmitter is also forwarded to the receiver along with the data lanes. That's thing. The clock forwarding architecture DCI interface uses clock forwarding and single-ended low voltage DDR signaling, to improve the power efficiency. Okay. So clocks generally, complementary. Though it's a single clock, but single-ended, single clock, but they are sent in two lanes, complementary to each other. Okay. Um, in addition to these, right, the main band also has two additional signals. One is track, one is hold. Sorry, one is valid, one is track. They provide control and synchronization information. Okay. So along with this main band, the both the architectures has sideband also, main band and sideband, right? Sideband, it has got again data, clock, signals, but handles low speed control and configuration functions. Now let's look into the third type, UCIe 3D. It offers a higher number, 80 single-ended data lanes. Okay, so the way the chiplets connected across each SoC with UCIe 3D is shown in the third diagram here. This one, okay, this one. Okay, where chiplet, since it's about vertical stacking, chiplet 0 is on, I mean, above the chiplet 1, the vertical connection. Reflections occur when a high-speed signal encounters an impedance mismatch. You can see the guy who is surfing, uh, okay, and just you can imagine an analogy with water. So the what when he's surfing, he immediately sees the infinite impedance or height difference, right? So the water reflects back, causing the water level changes in this region. Okay. Similar in a similar way, in the transmission line also you can imagine. Reflection occur when a high-speed signal encounters an impedance mismatch. A part of the signal is reflected back towards the source, the way current reflected back, right, towards the source, while the remaining part continues forward because it doesn't see infinite, mismatch, right? This reflected signal can interfere with the original signal, causing distortions, overshoot, undershoot, ringing effect. These effects degrade the signal integrity and can lead to system fluctuations. Okay, the termination is a technique used to prevent signal reflections by matching the impedance of the transmission line. For example, here this example, right? So by matching the impedance of the transmission line to the impedance of the either source or the load. Here in this example, for example, this is the impedance of the transmission line, assuming it is 50 ohms characteristic impedance, right? So the how we avoid reflections is by matching the source impedance to the transmission impedance, I mean like channel impedance, or okay, or okay, the matching this impedance with respect to the channel impedance so that there is no discontinuity in this part. Okay. Okay, so there are different kinds of the terminations. Generally, series termination is used at the transmitter side or near end or at the output of the driver. There are four kinds of terminations which are used in the far end or at the input of the receiver or at the end of the transmission line. We'll see it later. So the example of transmission series termination at the transmitter side is this way. Okay, see here it is. This is a driver. Okay, and this is a transmission line. Okay, we have a series resistance. See, this is in series with transmission line. So then it's also called as stub series. I mean this is in series. This RS source impedance is in series with the transmission line, the stub series. Okay, the RSC stub. Okay, that series stub, I can say that. Okay, the series sub series transmission line is also called as a source, you know source series, termination. The RSC is in series with transmission line. Okay, SST L or SST. Okay, So in the let's talk about with the specific to UCIe here. UCIe, the specification implies, UCIe spec applies a different termination schemes for advanced and standard packages to optimize the performance and cost. Okay, so now in this here we are only looking at the transmission side termination, that is a series termination. It implies series termination, the series with respect to the transmission line. The stub is in series with transmission line. Stub means RS here, series impedance, right? The impedance package. The transmit, what it UCI specs, mandates the transmitter driver strength control. The strength in the sense, for all the reasons, you have a 30 ohms in that path. Okay, that decides how much current you launch. That's one way to look at it. Okay, so the package needs transmitter side or source side impedance of 25 ohms. Of course, we it can go here and there plus or minus 3 ohms, but 25 is what is typical condition. Okay, for advanced package, the source impedance is 25 ohms plus or minus 3. Whereas for standard package, it is 30 ohms plus or minus 3 ohms. Okay, it can vary from 27 to 33. That's the spec, accepted UCI spec. How it is implemented here is this. Here is a pad. Okay, and this, of course, through bump it connects to the channel. Okay, and it goes to the receiver also. Okay, right. So now assuming this is a 50 ohms, right, characteristic impedance. Okay, how it is implemented? Ideally, this in the ideal situation it looks like this, but practically what happens is this becomes a part of the driver directly. They merge these two part and call it as a driver side. So this is how it looks like. Okay, from this path to this path it will be 30 ohms. So it means that 30 ohms, assuming you're launching logic 1. Okay, it means the total resistance is now with Rn of this resistance plus this resistance. Okay, so generally we have the habit of taking 20:80, but it all depends on how much size M1 end up. Okay, you ideally, okay, so yeah, M1 Rn resistance M1 changes a lot across PVT, so we don't afford to use all the resistance with M1 because we change a lot. That's the reason we go for RS. But then if you go all the reasons for RS, uh, okay, but you want to reduce M1 much smaller, so it will end up huge MOSFET sizes, right? So we have to find the balance between the actual resistance, the passive resistance and the Rn resistance of the M1. Okay, find the balance. What is the ratio here? The same thing is applicable for when you launch 0. So the total resistance here should be 30 ohms for standard package. Okay, of course it can vary plus or minus 3 ohms here and there. Okay, this is a source side termination or near end termination or termination, series termination at the driver side. Let's continue how the receiver termination is different from two packages. Okay, so this is how we know that, right? Reflection happens. High speed signals are susceptible to the reflections when the impedance is not continuous from the source to the channel to the receiver. Okay, so ideally what we want to do is we want to match the source impedance to the channel impedance, and we want to match the load impedance to the channel impedance, the line impedance. Both line and channel impedance are both same, right? So now we discussed in the source side or near side, the transmitter, right? Now let's talk about far end termination, or we can call it as a far end termination. We can call it as a termination at the receiver side. Okay, so at the receiver, we can do the termination by 4 ways, and those are parallel terminations, pull-up termination, AC termination, and Thevenin termination. Okay, so Thevenin termination, parallel termination, AC termination. What this UCIe, what we predominantly get to see here is the parallel termination. Each has their own advantages and disadvantages. Parallel termination is what we get to see here. Okay, the way it is like this. Okay, so now we have this 50 ohms, and the resistance impedance looking at this point is again 50 ohms. This way you can look at it. Okay, um, this is in general 4 theories, right? The 4 kinds of terminations on the far end, right? So how it is really implemented here, right, is this way. So I assume it is all of that single-ended for all the reasons. Okay, terminations are, sorry, signals are single-ended, clock is single-ended, data are single-ended. So naturally we go for a termination from this the signal, say data, to the ground. This is a parallel termination we call it as, and this value is typically 50 ohms. The same thing is applicable for clock, same thing applicable for track and valid and other signals. 50 ohms to the ground from the input of the receiver to the ground, or at the end of the transmission line to the ground. Both are same. uh, Okay, so now let's look at the actual values. Rx termination is applicable only to the standard package modules. This is the difference we get to say. Rx termination or foreign termination is applicable only to the standard package modules. Okay, the standard package requires Rx termination, and 50 ohm parallel termination to the ground is used. The way I showed it here, right? For advanced package, the Rx is unterminated. Because why we don't terminate? Because it needs higher performance and flexibility. The moment we terminate, it will affect the performance and flexibility and power. Let's look into the speed per lane and the bandwidth for each of the package types. So UCIe 2.0 spec document supports the following uh, speeds per lane. Minimum is 4 gigatransfers per second. The maximum is 32 gigatransfers per second for UCIe standard and UCIe advanced, both. Okay. In between, the standard transfers recommended is 8 giga, 12 giga, 16 giga, and 24 giga transfers per second. For UCIe 3D, UCIe 2.0 spec mentions 4 giga transfers per second. But the very goal of UCIe 3D is different. Here it's more towards application is more towards vertical stacking of the dice or 3D packaging. Okay, supported speeds per lane. Let's see the meaning of it, right? The supported speeds per lane it's about capability or maximum data transfer rate in a single lane. Okay, it's measured in gigabits per second or gigatransfers per second. Okay, we understood what is the meaning of speeds per lane, right? For example, what is the meaning by speeds per lane is standard package is 16 lanes. Each lane, how much data it can transfer. Advanced package is 64 lanes. Okay, and the 3D package is 80 lanes. So we are not talking about sum of all. We are talking about each lane. What is the maximum data is capability of data transfer. So let's look into the bandwidth now. Bandwidth is about the total data transfer capacity of the entire UCIe package. Okay, it is calculated by multiplying supported speed per lane by the number of active lanes. Okay, measured in gigabits per second. Okay, example, if there are 16 lanes in active for a standard package, for example, and all lanes are active. Okay, and the maximum data transfer rate is 32 giga transfers per second. Then the bandwidth here is 512 gigabits per second. Okay, the total bandwidth. Now let's focus more into the actual packages. Standard package UCIe, yes, often used in applications with a moderate and performance with moderated performance requirements, and the applications where the channel reach is is longer. For example, it supports 10 short and 25 long reach, right? What is the bandwidth? The maximum achievable bandwidth in standard package is 512 giga transfers per second. It is obtained by multiplying speed per lane and number of lanes, 32 into 16. Okay. Let's look into the advanced package now. It targets high performing applications demanding exceptional bandwidth. So the reach here is channel reach is very smaller to up to 22 mm. Okay, the bandwidth, the maximum bandwidth achievable in this case is uh, 2 tera transfers per second, which is obtained by maximum transfer per second 32 and number of lanes 64 for advanced package. Okay, the third type is 3D. 3D, the speed per lane is now fixed in 4 giga transfers per second, and the number of lanes is 80. So the maximum is 4 into 8 is 320 giga transfer per second is the maximum bandwidth achievable by 3D um, package. You see 3D. Okay, couple of things to discuss here. For example, the speed per lane depends on the transfer, transmitter capacitance, of course, in the receiver capacitance. Okay, the transmitter pad capacitance uh, here, right, for example, is um, 300 femto for standard package. Okay, if you want to use standard package at say 32 gigatransfers per second, then the speed will be then the effective capacitance will be 125 femtofarad. So if you see what is the effective capacitance now decides the speed you want to achieve. Okay, and it's captured in the image as a table. One thing. Second thing is that number of lanes decides the bandwidth of it. So the more number of lanes, more the bandwidth. But the number of lanes again decided by the kind of packaging you're going for. The standard packaging uses C4 where the bump pitch is quite bigger and you hardly have a less number of lanes and the density is lesser. Okay, for advanced package you have 64 lanes, and so you can achieve a bigger bandwidth. Let's see what are the transmitter and receiver pad capacitances defined by the UCE spec to achieve the required speed per lane and the overall bandwidth. So UCE spec document, right, supports the following speeds. If the minimum is 4 gigatransfer, maximum is 32 gigatransfer for UCE S and A. That, right? So and it mentions 4 gigatransfer per second for 3D version of it. So now see, and pad capacitance plays a critical role in achieving these speeds, and we have to limit the pad capacitance, effective pad capacitance. Okay, at the pad, the effective capacitance at the pad, we have to limit this to achieve the required speed. Okay, so what is the maximum of effective capacitance? What the UCS spec document talks mentions is captured in the first table here. For all the speeds, for advanced package, for all the speeds, the pad capacitance the document mentions is 250 femtofarad. So, whereas for 8 gigatransfers per second, for standard package, 300 femto is good enough. Okay, and for and for 16 gigatransfers per second, for standard package we have a 200 femto. For 32 gigatransfers per second, we need to achieve maximum we can see the effective capacity of the pad is 125 femtofarad. Okay, so now it's very clear from this table, right? For standard package, the maximum or the effective capacitance which we can see at the pad is speed dependent, which can go as low as which can go up to 300 for 8 gigatransfers per second, 125 femto for 32 gigatransfers per second. For advanced package, for all the speeds, 250 is the maximum ACA spec allows. Similarly, the receiver pad capacitance also very important for achieving the speed. Okay, so again here for advanced package, 200 femto is fixed. Okay, for all speeds. Okay, so whereas say with similar to the transmitter side, for standard package, receiver also mentions the effective capacitance as a speed dependent. For example, up to 8 gigatransfers per second, 300 is femto is allowed, and up to 30, for 24 and 32 gigatransfers, 120 femto is allowed. Okay, more than that, it will hamper the speed. So there are many more differences between the three packages: standard, advanced, and 3D. Uh, let's consider them in our next sessions. Thank you for your interest.